In the last lecture, we had started to discuss about unit testing. We looked at some aspects of unit testing, the stubs and drivers. The stubs and driver are small software that needs to be written by the testers before they can start carrying out the unit testing. And of course, the unit testing is done by the developer themselves, and therefore, these are the developers who do unit testing, and therefore, they write the stubs and drivers. The independent testers, they do the integration and system testing, who are part of the test team, and the unit testing is performed by the developers themselves, and before they can unit test unit, they need to write the drivers and stubs and then carry out the unit testing. Now, let us look at more detail into unit testing. How does one design unit test cases? Let us say we want to do unit testing for a function. As I was mentioning, that unit testing can also be done for a module or for a class or for a component, but let us now assume that we are interested to do unit testing for a function. Now, what are the main approaches to design unit test cases? One is called as the black box approach. The other is white box approach, and the third is gray box approach. For a function, unit testing is basically a black box and white box. We will see how to design those test cases and why these are called black box and white box. But for a class or a module or a component, we might also have to do a gray box approach. In black box approach, we do not need to know the entire detail of the software. We just view the unit as a black box. This is our unit. We just know that if we give input to the black box unit, it should behave in some way, in the sense that it will produce some output. So, the black box approach, we design the test cases by observing the inputs that should be given and the output that should be produced. On the other hand, in the white box or glass box approach, we know the details of the code that is there, and therefore, we can create a model of the code, for example, a control flow diagram or something, and then based on the internal knowledge of the code, we might design some test cases. So, this is called as a glass box, because we need to check the internal code. Here we do not even bother about what is the code, we just look at its specification, that is what is the input and what output should be produced, and based on that we design the test case. On the other hand, in the gray box approach, we have something in between a black box and a white box. We use the design of the unit, maybe a class diagram, maybe a state model, a class diagram, or maybe a call relation between modules, and so on. So, these are the design models which are intermediate between a black box and white box. You do not really need to look at the code, and neither is it a black box. We have knowledge which is intermediate between a black box and a white box, and that is why it is called as a gray box. and if it is a pure function that we are testing, we need to test only black box and white box, but for classes, components and so on, we might have to do a gray box testing as well. Now, first let us do black box unit testing. The black box unit testing is done based on the functional specification of the software. Or functional specification of the unit. So, given a unit, and then we do not need to look at the code, we just see what is its input output behavior, and based on that we design the test cases. We should not look at the internal of the software, only the input output behavior. The black box testing is also called as functional testing, because based on the knowledge of the functionality, without looking at the code we test it. So, it is also called as the functional testing. Now, let us try to appreciate why black box testing can be hard. Here we just look at the input data and the output behavior, that is what it should output, and then design test cases. The main complexity here is that the data domain for any typical software is large, and therefore, we need to decide which test cases to apply, because we need to have an optimal number of test cases, and we have to select that out of the billions or trillions of test data that are possible. And not only that, a function may take multiple parameters. So, we need to fix the values of those parameters. So, if a function takes just one parameter, we need to just test with respect to that parameter. But if it takes two parameters, and there are number of values that are possible for this parameter and for this parameter parameter 1 and parameter 2 for a function, then we have to possibly test with various combinations of values, maybe fix this as this and test with respect to this, maybe fix these and test with respect to this, and so on. So, we need to try out various combinations, and that makes testing much more challenging and complex. First, let us convince ourselves that even a very small function, just a 2-line function, can become extremely hard to test if we want to do the black box testing thoroughly, that is exhaustive black box testing with all possible input values. Let us consider a very trivial function. Name of the function is check equal. Takes two integer parameters and then checks if these two parameters are the same. Basically, just one liner here. If x equal to y, return 1, else return 0. But then we are not looking at the internals, we are just doing a black box testing. So, what we will do is we will check whether this function works well for all possible combinations of input data. Now, let us say we are using a 64-bit computer. In a 64-bit computer, each integer is represented using 64-bit, and for simplicity, let us assume, because integer representation we do not want to go that level, but we just say that 64 bits are used, and therefore 2 to the power 64 inputs are possible for the first parameter. Similarly, for the second parameter 2 to the power 64 different inputs are possible, and therefore the total number of inputs with which the function needs to be checked is all possible combinations of the first parameter and the second parameter, which is 2 into 2 to the power 64 is equal to 2 to the power 128, and this is a huge number. We can read 2 to the power 10, 2 to the power 20, 2 to the power 30, but I can't even read what is 2 to the power 128. It is extremely large. 2 to the power 10 is kilo, 20 is million, 30 is billion, trillion, and so on. I don't even know how to read it. It's extremely large number, and let's assume that we are testing manually this 2 to the power 110, 28 possible values with which we need to test, and let's say that we are expert in typing, can type very fast and just take 10 seconds to enter each test data. And if we compute that, the number of hours that will come here is very large, and we can easily compute how many hours, and then we might take a billion year to enter all possible values, and that is just to test this small program. And therefore, the black box testing is hard if we consider all possible inputs, but our objective now is to find out black box test strategies which will drastically reduce the number of test cases, maybe 3, 4 or something, but then they should be almost as effective as exhaustive testing. So, that is our objective. With that objective, let us see what are the test strategies that we have. In all these test strategies that we discuss, we will create a model of the data domain, because we know the input data, the output data. We will create a data model, and based on the data model, we will design the test cases. On the other hand, in the white box testing, we know the internal structure, that is the code we can check, and therefore, it is also called as structural testing, because we know the structure of the software. Now, let us look at black box testing before, and after that we will look at white box testing. In black box testing, we look at the system as a black box, and then we know the input output behavior. It is also called as data driven testing or input output testing. We look at this first, and we have already seen that exhaustive testing is very difficult. We need to have some test strategies which are almost comparable with respect to the effectiveness or thoroughness of testing of the exhaustive testing, but the number of test cases should be much less and should take very less effort compared to exhaustive testing. There are a large number of black box test strategies that have been reported. We will look at only few of them: the scenario coverage, equivalence class partitioning, boundary value testing, cause effect testing, combinatorial and orthogonal array testing. First, let us look at the scenario based testing. From our discussion on scenarios, which we had during the object oriented discussion on object oriented design, we know that a use case consists of many scenarios. One is called as the main scenario, and then we have the alternate scenarios. At some point in the main scenario, the alternate flows occur, and these may actually end, or they might just have a separate set of actions and then have similar action as the main line. Now, if this is a kind of description of a use case with different scenarios, then how do we design the scenario based testing? The first thing is to identify the use case scenarios, and typically if our requirements document is well written, we will have identified the scenarios there in the form of a text description, and for each scenario we will identify one or more test cases, and these test cases are actually will execute the scenarios, and then we identify the test data, and then also identify the state at which the system should be there for the test data to be entered, and that we say that identify the conditions that will cause this to execute, and then complete the test cases by adding the data values. If we represent our scenarios in this form, that first is a basic flow, then basic flow with alternate flow 1, alternate flow 1 with alternate flow 2, etc. We develop the table, and then each of these are a scenario, and we need to have that many test cases, and for each scenario we need to identify the conditions or the state at which the input to be given, the data input values, there may be many inputs to be given, the expected result for each of the input, and the actual result that was observed. Let us look at the next black box testing. The scenario coverage was rather intuitive and straightforward. Just identify all the scenarios by looking at the SRS document, and then we just list out all the scenarios and then the condition under which these will execute, and then the test data and the expected output. Now, let us look at the equivalence class testing. This is another black box testing. In this approach, we look at the input data domain and then we partition it into equivalence class. The main idea behind partitioning the input data into equivalence class is that the program will behave similar way for every input belonging to an input equivalence class. So, if this is the set of input to the unit, we identify equivalence classes in the input, and the main idea here is that for this, let us say equivalence class 1. So, this is the set of data set or the data domain of the function, and then we have partitioned it into equivalence classes 1, 2, 3, 4, etc. And for each equivalence class, all input should execute the software in similar way. That is, the same set of statements may get executed. Of course, here we do not have a knowledge of the internal of the software, but just by observing the behavior, we can guess that these are executed in similar manner. And from each equivalence class, we select one value with which to test, and if the scenarios are extremely simple, then each scenario need one equivalence class, but then it is much more complicated. Normally every scenario might need hundreds of equivalence classes or thousands of equivalence classes. So, we need to pick a value from each equivalence class. One of the main assumption in equivalence class is that we want to reduce the number of test cases with which the system needs to be tested, and if these are all the set of test cases that are possible in exhaustive testing, we have partitioned it into equivalence classes E1, E2 and E3, and the way we have partitioned into E1, E2 and E3 is that each element in equivalence class E1, they behave similarly, the system executes similarly for each of the input. So, if we execute one of the data here, then we have tested that behavior of the unit. So, our work now becomes to test with one representative value from each equivalence class. And defining the equivalence class really helps, because testing using one value is equivalent to testing any other value in that equivalence class, and each equivalence class typically may contain thousands or millions of data points. We are assuming that executing using one of these points, since the behavior is similar, it is same as executing all of them, and therefore, the equivalence class testing drastically reduces the number of test cases. But then, even though it is a very good technique, effective technique, and reduces the number of test cases drastically, but the question that we are confronted is that how does one go about identifying the equivalence classes? One is, we need to identify the scenarios, we need to examine the input data, we need to examine the output data, and then based on this we need to design the equivalence classes. But then that is a bit of a vague statement. Can we tell something more concrete? We will give that in the form of a few guidelines. The guideline is that if the input data is a range, we will have two immediate equivalence classes. One is a valid and two invalid. So, the range is 1 to 100. Anything between 1 to 100 is a valid data, and anything more than 100 is invalid, and anything less than 100 is invalid. So, we have one valid equivalence class and one invalid equivalence class which contains values less than the minimum value that is acceptable, and one which has values higher than the highest value that is acceptable. So, there are two invalid equivalence classes and one valid equivalence class. If the input is a set of data, like let us say A, B, C, these are all valid data, the system will respond to this. But then we have invalid data which are not part of this set. Anything that is not part of this set is an invalid equivalence class. So, for a set of data, we have two equivalence classes, one valid and one invalid. Valid belongs to the set, invalid is anything other than that. If the input condition is a Boolean, again we have one valid and one invalid, that is, we give a Boolean value or do not give a Boolean value. Just to give some example, if we want to enter a area code, let us say the area code is between 10,000 and 90,000. So, the valid values are between these two, and then anything more than 90,000 are invalid, anything less than 10,000 are invalid. So, 1 valid and 2 invalid. What about a password which contains 6 characters, a string of 6 characters? The set of the password containing 6 character in a string of 6 characters, we can consider it as a set of values. So, all those strings which contain 6 characters, they are the set of values. So, we have one valid password which is any of these members of this set, and the invalid password which is not part of this, maybe it contains 5 characters or something, or maybe a special character. Now, let us look at an example. How do we do equivalence class partitioning? Let us say we have given 3 sides of a triangle, and we want to decide whether it is a isosceles, scalene, equilateral, etc. So, this is simple function. It takes argument 3 sides of a triangle and displays what is the type of the triangle, and we want to design equivalence class partitioning for this. Looking at the output here gives us the hint about the equivalence classes. So, all the data sets for which it will produce isosceles is equivalence class, scalene is another equivalence class, equilateral another class. So, here the equivalence classes are easily identifiable from the output, but for any input data we have always 2 equivalence classes, one is valid and one invalid, and there may be several invalid. So, to start with, there is one valid equivalence class and another invalid equivalence class, and we might have several invalid equivalence classes here, which we might later identify, and also there may be several valid equivalence classes out of this. So, given a problem to design the equivalence tests, we first define 2 equivalence classes, the valid and invalid, and then look at further division the valid into equivalence classes, set of equivalence classes, and each of these may again contain equivalence classes. We will just look at that in the next lecture. Right now, we are almost at the end of this lecture. We will stop here. Thank you.